Hi everyone, for this video we'll go through Project 3. There are two portions for Project 3. The first part is sorting and searching, and then the second part is hash tables. In the first portion, we will be implement two algorithms, which are quick sort and heap sort. And we're going to test our implementation as follows. For me, I modified the code from the textbook data structures and program design in C++ by Cruz and Reba. So here are my modified code. I create a class called sortable list, and here are some basic things like constructor and compute assignment operator. Let's begin with quick sort algorithm. The first function that we needed for quick sort is partition, which we make left side of the pivot be the value that are less than the pivot, and the right side of the pivot be the value that are greater than the pivot. So here is how we do it. We make our first entry the pivot and the index be our last mode, and we walk through the whole list. So as we have a value that are less than the pivot, the last mode index will increase by 1, and we swap the values in last mode index with the I. And since we need to compute the number of comparison operation, we add an operation here. At the end, we're gonna swap the low value with the last mode value. So we're gonna put the pivot into its proper position. Next, we have our function recursive quick sort. So in this function, the entries in the list will be rearranged so the keys are sorted into non-decreasing order. Lastly, we have our quick sort, the method that we're gonna use in the main function. And the quick sort gonna just implement recursive quick sort, but in quick sort we have no parameters. So the first function that we needed for heap sort is insert heap. For this function, we know that root will always be the largest key. So when we move the largest key from the first to the last entry of the list, the root will be emptied out. And in this case, we need to promote entry through the GCs until the second largest key become the root. And we then remove this root value into the last entries. And we're just gonna repeat this algorithm. After that, we also need to build heap. So we need to building the heap in order to do the insert heap. And our heap sort method will implement the build heap, insert heap to arrange all the entries in the correct order. To check our algorithms, we have pseudocodes for our test case. So we're gonna first generate 5,000 random integer between 0 to 10 to the power of 6, and we're gonna store them into a temporary array, and we're gonna create another two arrays that store the values in the temporary array, and then we will use the methods that we created before to quick sort and heap sort them. And since our goal is to know the comparison operations for them, we just create an array to store the number of comparison operations in each child. After we finish the trials, we start to find the minimum and the maximum and compute the mean, the median, and the standard deviation of the number of operations in quick sort and heap sort. So these are the outputs from my code of the test case. Here are the number of comparison operations for quick sort, and these are the heap sort. So I set the number of child 30. So as we can see, we have 30 values for each of them. And we can observe that the quick sorts have less number of comparison operation than the heap sort. Second portion of project 3 are hash tables, which we will store integers based on linear probing and quadratic probing. And we're gonna do our test cases for this one also. So in this part, we will have some example codes show us how the hash table is working. So this is the example for hashing a 6-character long string, and this is an example of hashing a 6-digit integers. And we can see that's how we implement them, the function, and the outputs for them. So here are my codes for hash table is quite simple. So for the linear probe, we need to increase the index by 1 and model size, so we will be able to wrap around to the beginning of the table if we reach the end. And then we insert this key value pair into the empty slot that we found. And for quadratic probe, we need to increase the index by its square value. So index plus I squared and mod the size. So it will be able to wrap around. And then we just insert the value into the empty slot that we found also. Since we need to find the probe count, so we do a probe count here to count the probe that we have. For the test case of our hash table, we just need to insert 4,000 random integer into the hash table for each child, and then for each child, we're gonna just perform the linear probe and the quadratic probe to them, and then collect the probe count that we have, and in the end, we're just gonna calculate the average for those values. So here are my outputs for each child. As we can see, we have 10 childs, and each child we display the number of linear probes and the number of quadratic probes. Then we compute the average of these 10 childs, and we will find those two values. And from those two values, we can see the quadratic probe is less than the linear probes. So we may say that the quadratic probes is more efficient than linear probes in the hash table. So this is the end of project 3, and thank you for watching.